In the previous start over. In the previous module, we took a look at point estimates as a way to estimate parameters of the distribution, but that didn't allow us to make any sort of statement about the confidence that we had in regarding the parameter estimates. So here we're going to turn to intervals to doing just that sort of thing. And we'll continue on with an example similar to what we've been using, and that is that x, or random variable, is going to be associated with fatigue life of a material. In this instance, that's going to be on the order of millions of cycles to failure. And we've done collection of data off of 16 specimens where our sample mean was 26.75 millions of cycles, and our interest then is the population measure, not of the sample mean, but rather of just the underlying random variable x, and asking the question, how good an estimate is x bar? That we used x bar, the sample average, as an unbiased estimator of u, and it was also the estimator out of method of moments, and it was also the estimator of choice out of the maximum likelihood method. So one of the keys in this kind of approach is to understand two different perspectives, and that's the before sampling and after sampling view of the world. Where before we've done any sampling, the expected value of our sample mean is equal to our population measure, and the variance of our sample mean was equal to the population variance divided by n. And the sampling distribution for x bar is approximately normal, so long as n is large, and that might be on the order of 30 to 40 depending on your perspective. I've talked before in the previous module, for instance, that n greater than 30 is one commonly accepted number. Your textbook authors, Montgomery and Runger, prefer 40, and there are even plenty of instances where this number can be as low as 20, and even maybe slightly smaller than that to be approximately normal. It all depends on the underlying distribution and how normal-like it is to begin with. Okay, and so one of the things we're going to be driving for here is we want the probability that the true mean is between two limits, and that probability is a given value. And so then the question becomes, what are the two constants a and b? And now, key emphasis here, this is before sampling, and when we take a look at this after sampling, there's going to be a key different interpretation of this kind of a statement. Right now, we're looking at, well, what's the likelihood that the true mean is between two different values, a and b, and we're going to start thinking about the influence of x bar, what kind of information that gives us. In fact, let's go directly right at that. Let's let a variable u be equal to x bar minus the mean of x bar divided by the standard deviation of x bar. We could have used z here. I've chosen to use u. You'll see a little bit y here in a second. And now we'll substitute in for each of those two values. It's x bar minus now the mean of x, because the expected value of the sample mean is the underlying population mean, and then sigma x bar is going to be sigma x divided by the square root of n. And u will have a standard normal distribution, mean 0 and standard deviation of 1. Okay, now that's a different view than after. So let's stick here with the before view as before sampling, and go more directly at this probability statement here, transforming this one that we had up here that we're going to look at now, the probability that this new transformed variable x bar minus the mean of x over sigma x divided by square root of n is between two bounds, u1 and u2, upper and lower bound. And we're going to set that equal to a specific probability value. That's a central value in this case. Right, we've got our normal curve and our probability value of 0.95, which is just a very commonly used value. There's your central value of 95%. Right? And again, this before view here, we're considering that we have a symmetric distribution. It's two-sided interval that we're going to end up with. Two-sided because we've got tails that are equal on either side. They don't have to be, but they commonly are. And for this then, our u1 value is going to be equal to the opposite of u2. And for that central value of 0.95, that means that we have tail value of 0.025 on either side. And it also means that our u values are going to be u1 equals minus 1.96 and u2 equals a plus 1.96 from the standard normal tables. Okay, so if we go back to our probability statement here, then we get 0.95 equals the probability that, and now we're going to isolate x bar in the middle of this. Right, so we'll multiply through on both sides, so that means the u1 value becomes u1 sigma x over square root of n, and then we're going to take the mu x out, and we'll have mu x plus u1 over that, and then we'll have x bar in the middle, and then likewise we'll have mu x plus u2 sigma x over square root of n. Right, now we'll just go ahead and substitute in our, for u value, 0.95 equal probability of mu x minus 1.96 sigma x over square root of n less than and mu x plus 1.96 sigma x over square root of n. Right, and emphasize here, that's the before view. Before we've done the random sample, we're saying that with 95% probability, the sample mean will be between this lower bound and this upper bound value. Right, now that's not the same view as when we go and take a look after sampling. where now we're going to develop a confidence interval on the true mean rather than a prediction interval associated with the sample mean. And what we end up really doing is reversing roles that back up here where we solved for x bar. We're going to instead solve from ux. And note there's a minus sign here, so in a certain sense these two are going to swap locations, u1 and u2, because of that that minus sign that's there. And our confidence interval now is going to come from probability that x bar minus 1.96 sigma x over square root of n is less than mu x is less than x bar plus 1.96 sigma x over square root of n. And that's for a very specific value of the confidence level of 95%. Okay, so back to our example, where our x bar was 26.75, we had n equal to 16, but we have a problem, and that is, what is sigma x? And for the moment, let's assume that it's equal to 20. So we have a rather large COV, and that is often the case in these fatigue types of problems that we might have that. And so now in this case, when we substitute in these numbers, n equal to 16, our 0.95 equal to p of 26.75 minus 1.96 times 20 over the square root of 16, right, less than mu x less than 26.75 plus 1.96 times 20 over square root of 16. And we'll get here 16.95, and over here we'll get 36.55 as our confidence interval for the true mean. Okay, note this exceptionally large interval that we're getting in this particular case. And in the next segment, we're going to talk about interpretation of this and a cautionary tale of woe about how you could misinterpret what this confidence interval means.